Hello everyone and welcome back to PHYMICS. This is part 3 of our quadratic polynomial series. In the first part, we have learned what a quadratic polynomial is and its standard form. In the second part, we explored the relationship between zeros and the coefficients. And today, in the third part, we will finally learn how to solve these zeros step by step. Since a quadratic polynomial is in the form px equals to ax square plus bx plus c, where a is not equal to 0. The zeros are the values of x for which the polynomial becomes 0, or simply where the graph cuts the x-axis. So let's solve the graphical problems from the NCERT. This is a classic NCERT problem in which the polynomials are represented graphically. We need to find how many zeros does each polynomial have. We know that graphically the zeros are represented on x-intercepts, as on x-axis y becomes 0. So to solve such problems, we just need to inspect the graph where it cuts the x-axis. In the first figure, the line is parallel to the x-axis. Since the graph does not cut the x-axis at any point, therefore it has no zeros. In the second figure, the graph dips and then rises, cutting the x-axis once on the right. Therefore, it has only one zero. In the third figure, the graph crosses on the left, goes above, comes down and crosses again, dips below, then rises and crosses a third time. So it has 3 zeros. In the next one, the parabola cuts the x-axis at 2 distinct points. Therefore, it has 2 zeros. In the fifth figure, the graph cuts the x-axis 4 times, thus there are 4 zeros. In the last figure, the graph cuts the x-axis once from the left, then touches the x-axis and later again touches at right, therefore it has 3 zeros. Now to find the zeros of the quadratic polynomial by algebraic methods, we have factorization method, completing square method, which on generalization gives a new method called quadratic formula. In case you don't know what factorization is, you can click on the I button. Since factorization is a process of expressing a given expression as a product of its factors, therefore there are various techniques through which factorization can be done. One must try the easiest technique first, and if it fails, then only moves to the advanced one. In order to factorize, the general guidelines will be using the direct common method first. If it fails, move to the grouping method, followed by the identities, and later on the factor theorem. Let's solve the problem of NCERT by factorization method. Let the given polynomial be px equals to x square minus 2x minus 8, which is in the standard form of ax square plus bx plus c. Now to find the values of x for which this polynomial becomes 0, just equate it to 0. Since different terms can't be simplified to give 0, so we are just left with only one option, that is to factorize. That is, expressing the polynomial as the product of its factors. Since by inspection, direct common method fails, so moving to the grouping method, we see the number of terms are odd, and thus grouping method also fails. But in case of quadratic polynomial, we have solution to this problem called splitting the middle term. Under this, multiply the first and the last term of the polynomial px, that is x square into minus 8. Now by hit and trial, think of two numbers using the factors of 8x square whose sum equals minus 2x. Therefore px becomes x square minus 4x plus 2x minus 8 equals to 0. Now the terms are even in the number, and thus the groups of first two terms and the last two terms are formed. Now taking the common factors from each group, we get x into x minus 4 plus 2 into x minus 4 equals to 0. It should be noted that if the sign of the first factor matches with the sign of the last term, then the common factor with positive sign is considered from the second group. In case the signs do not match, the common factor with negative sign is considered. Now taking x minus 4 as common factor from both the groups, we get x minus 4 into x plus 2 equals to 0. Since anything multiplied by 0 is 0, therefore equating each factors to 0, we get x equals to 4 and x equals to minus 2. So 4 and minus 2 are the zeros of the given polynomial px. To verify the relationship between zeros and the coefficients, we have a equals to 1, b equals to minus 2 and c equals to minus 8. We know that the sum of the zeros equals minus b upon a. By solving the LHS, we get 2, and by putting the corresponding values on RHS, we get 2. Also, the product of zeros equals to c by a. Similarly, by solving the LHS and RHS independently, we get minus 8. Hence, the relationship is verified. Moving on to the second problem. Let the polynomial be ps equals to 4s square minus 4s plus 1. Now to find the zeros, just equate ps equals to 0. By inspection method, direct common method fails. Since it is a quadratic polynomial, so by using the splitting middle term, we get ps equals to 4s square minus 2s plus 1. Now by grouping method, taking 2 as common factor from first group and minus 1 as common factor from the second group, we get 2s into 2s minus 1 into 2s minus 1 equals to 0. Taking 2s minus 1 as common factor from each group, we get 2s minus 1 into 2s minus 1 equals to 0. Since anything multiplied by 0 is 0, therefore equating each factor to 0 we get s equals to half and s equals to half, which are the required zeros. To verify the relationship between the zeros and the coefficients, we have a equals to 4, b equals to minus 4 and c equals to 1. We know that the sum of the zeros is equal to minus b upon a. By solving the LHS we get 1, and by putting the corresponding values on the RHS we also get 1. Also the product of the zeros is equal to c upon a. Similarly, by solving the LHS and RHS independently we get 1 by 4. Hence the relationship is verified. Moving on to the third problem. Let the polynomial be px equals to 6x square minus 3 minus 7x. Since it is not in the standard form, so by rearranging we get polynomial px equals to 6x square minus 7x minus 3. Now to find the zeros, just equate the polynomial px equals to 0. By inspection, direct common method fails. Since it is a quadratic polynomial, so by using the splitting middle term, polynomial px becomes 6x square minus 9x plus 2x minus 3. Now by grouping method, taking 3x as common factor from first group and positive 1 as a common factor from the second group, we get 3x into 2x minus 3 plus 1 into 2x minus 3 equals to 0. Taking 2x minus 3 as common factor from each group, we get 2x minus 3 into 3x plus 1 equals to 0. Since anything multiplied by 0 is 0, therefore equating each factors to 0 we get x as minus 3 by 2 and x equals to minus 1 by 3, which are the required zeros. To verify the relationship between zeros and the coefficients, we have a equals to 6, b is equal to minus 7 and c equals to minus 3. We know that the sum of the zeros is equal to minus b upon a. By solving the LHS we get 7 by 6, and by putting the corresponding values on the RHS we also get 7 by 6. Also the product of zeros is equal to c by a. Similarly, by solving the LHS and RHS independently we get minus half. And the relationship is verified. Moving on to the fourth problem. Let the polynomial be pu equals to 4u square plus 8u. Now to find the zeros, just equate the polynomial pu to 0. By inspection method, direct common method is applicable. Taking 4u as a common factor from both the terms, we get 4u equals to u plus 2 equals to 0. Since anything multiplied by 0 is 0, therefore equating each factor to 0 we get u equals to 0 and u equals to minus 2. To verify the relationship between the zeros and the coefficients, we have a equals to 4, b equals to 8 and c equals to 0. We know that the sum of the zeros is equal to minus p upon a. By solving the LHS we get minus 2, and by putting the corresponding values on the RHS we also get minus 2. Also the product of the zeros is equal to c by a. Similarly, by solving the LHS and RHS independently we get 0. Hence the relationship is verified. Moving on to the fifth problem. Let the polynomial be pt equals to t square minus 15. Now to find the zeros, just equate this polynomial pt equals to 0. By inspection, direct common method fails. Since there are only two terms with no common factor, so grouping method also fails. Now by reducing this given polynomial to the identity a square minus b square equals to a plus b into a minus b, we get polynomial pt equals to t square minus root of 15 whole square, which on further simplification becomes t plus root of 15 into t minus root of 15 equals to 0. Since anything multiplied by 0 is 0, therefore equating each factor to 0 we get x equals to negative root of 15 and x equal to positive root of 15, which are the required zeros. To verify the relationship between zeros and the coefficients, we have a equals to 1, b equals to 0 and c equals to 15. We know that the sum of the zeros is equal to minus b upon a. By solving the LHS we get 0, and by putting the corresponding values on the RHS we again get 0. Also the product of the zeros is equal to c by a. Similarly, by solving LHS and RHS independently we get minus 15. Hence the relationship is verified. Moving on to the sixth problem. Let the polynomial be px equals to 3x square minus x minus 4. Now to find the zeros, just equate this polynomial px equals to 0. By inspection, direct common method fails. Since it is a quadratic polynomial, so by using the splitting middle term we get px equals to 3x square minus 4x plus 3x minus 4. Now by grouping method, taking x as common factor from the first group and positive 1 as a common factor from the second group, we get x into 3x minus 4 plus 1 into 3x minus 4 equals to 0. Taking 3x minus 4 as common factor from each group, we get 3x minus 4 into x plus 1 equals to 0. Since anything multiplied by 0 is 0, therefore equating each factor to 0 we get x equals to 4 by 3 and x equal to minus 1. which are the required zeros. To verify the relationship between zeros and the coefficients, we have a equals to 3, b equals to -1 and c equals to -4. We know that the sum of the zeros is equal to -b upon a. By solving the LHS, we get 1 by 3. And by putting the corresponding values on the RHS, we also get 1 by 3. Also, the product of the zeros is equal to c by a. Similarly, by solving the LHS and RHS independently, we get -4 by 3. Hence, the relationship is verified. If you have not watched the part 1 and part 2 of this series, you can check the links in the description. In part 4, we are going to find the quadratic polynomial when its zeros are known. So stay tuned. See you in the next one. Thank you for watching.